All right, so last time we started taking a look at 14.6 cylindrical coordinates. Somebody tell me what you remember about what we've done so far. It's like polar coordinates, at least in 2 dimensions, right? What about the 3rd dimension? Like if we hold x and y as our polar coordinates change into polar coordinates, what do we do about z? Do you remember? Well, we treat it just like we would have before in rectangular coordinates. We don't do anything differently with z. I mentioned that sort of in that way because we're going to encounter another coordinate system in 14.7 where we're going to change all 3 coordinates instead of just 2 of them. Okay? So we're taking a look at cylindrical coordinates in this section, so making cylinder shapes. And as we did this, we did a couple examples where we simply just converted from rectangular coordinates into cylindrical coordinates, and these were equations where we did that. And then we took a look at example number 3, where we set up a triple integral, but we didn't solve it. Does that sound right?
Yes.
And we were done with 3 and ready to 4. Yes? Okay, so we simply were looking at finding out what are the limits of integration on this, and you wanted to remember that when you change this into polar or into cylindrical coordinates, you have the r involved in this, just like when you did polar coordinates and it became r dr d theta. Okay? All right, so we're going to do another, well, the directions are the same, so we're going to set up the triple integral, and we're going to do another example like that. All right, so here is our region. This is example 4. Q is the solid bounded by y equals the square root of x squared plus z squared and y equal to 9. So I mentioned in the last problem, I'm going to jot this down, but I'm going to flip back to the last example to show you something. I mentioned in the last problem that we get to choose which 2 variables we replace for r and theta. In this particular one right here, it was nice to replace the x and the y because we have x squared plus y squared, so we can let that be r squared. But there's nothing special about x and y doing that. We could let any of the 2 variables have that feature. So if you take a look on this example, we've got x squared plus z squared underneath my radical, right? So in this one, I'm not going to replace x and y with r, so to speak, r and theta. I'm going to replace x and z with r and theta. Everybody good with that so far? I mean, it's just that it's setting along a different axis is the only difference. So right here is going to be my r value, right? So this actually tells us then that y is going to equal r. All right, square root of r squared, so we get r. We also have a bound here for y equal to 9. That's actually a nice feature. So we actually have the conditions on y automatically for ourselves, right? Y goes from 9 to r, and that's going to be my innermost values. So if y is equal to r, then r is equal to the 9 as well. Let me say it that way over here. Oh no, I didn't write that right. I said that wrong. Let me get this down. Okay, here's my triple integral of f of x, y, z dv. I'm going to have 3 integrations. We talked last time about the order of this always sort of matching. It's always going to be the same. The order is going to be, well, it's going to have an r in it, and it's going to be dy, dr, d theta. So whatever the rectangular coordinate is that is not changing is going to be on the innermost integration, and then dr, d theta. So my function here will be in terms of, instead of in terms of x, y, z, it'll be in terms of r, theta, and y in this case, not in that order necessarily. But we can take a look over here at how this is described, and we can take what we have from before. So in polar coordinates, what does x equal? What is the conversion equation? R cosine theta. Now, in this particular problem, we are not changing y, so y is still going to be y. So what do you think z is going to be given that information? That's going to be the r sine theta. It's not coming through very clear today. It's r sine theta. Yes, z is r sine theta. I'm going to try that again. You can't even read it. That's better, yeah? R sine theta. Okay, great. Right, so we're going to always have one of the variables still in there. And so if it's x that's still in there, well, we can let, z be r cosine theta. So we can make the conversions however we choose. We've just got a fixed way of making them in general that we've used before because we were only changing two variables. We didn't have a third variable as an option. So here it's going to change things a little bit. So my limits of integration on y are the ones that I found in red above, right? The y goes from 9, is between 9 and r. Okay? And so we're going to go from r up to 9. What about r? What does r have as its limits of integration? What's the smallest that r can be? I mean, take a look at the equations where we had them set up before. What is the restriction on r? 0, right? This equation right here tells me that the original one that I was given, that y can't be negative, right? Because it's a square root. So the lower limit of integration for that would be 0. And what would the upper limit of integration then be for r? 9. Over here, remember, r is equal to y, which we have equal to 9. So it's actually 9 as well. What about theta? Any thoughts on theta? 0 to 2 pi, why? Because it's theta. Well, there's something of that. I mean, we do have it going between like angle measures, right? But why would 0 to 2 pi be the right angle measures that would be making sense for us? This is circular. I mean, the region that we're looking at has a circular shape to it, right? So this is our function that we would be integrating if we actually had an equation. We don't have an equation on this one, but this is the setup that we were looking for. We're going to do one more. Okay, number 5. So Q is the solid bounded by the hyperboloid x squared minus y squared minus z squared equals 1, where x is greater than 0, and x equal 4. I mean, x squared, y squared, and z squared are all, x and y and z are all squared, but there's something weird about this one that didn't happen with the others. What is it? X squared is what, Caleb? The x value is 0. That didn't happen, but I'm talking about with the squared. This equation right here, when I'm making my decision, I have to make a decision which variables to replace with r and theta. What's weird about this, though, is that I have two negatives, correct? I don't have an x squared plus a y squared or an x squared plus a z squared. So what am I going to have to do? There is something that we can do to fix that, so to speak. For which one? Right. So what we can actually do is think about this as though this really says x squared, basically minus y squared plus z squared. So I am going to have a minus r squared, yes. Right? Because I basically have a negative on two of them. So the variable that I'm going to actually leave fixed in this one is x. It's the y squared and the z squared that are going to be replaced with r squared. So this equation actually becomes x squared minus r squared equals 1. And we'll keep working with this to solve it for r. So if I want to solve this equation for r, what am I going to get? Or I'm sorry, not for r, for x, what am I going to get? X equals the square root of 1 plus r squared. There we go. All right, so for my triple integral that I'm working with, in terms of my function itself, I've got a function where I'm leaving x fixed. And then I'm going to do r cosine theta and r sine theta. And it really doesn't matter which one I pick. So I'm just going to do them in the standard order with cosine first and sine second. If you switched them around, it wouldn't hurt anything. Okay, it would be fine. But we're going to do r cosine theta, r sine theta. And then what do I need at the end of this? An r, good, and then what will come after my r? Dx, which is always first, and then dr, and then d theta, right? Okay, so now what are my limits of integration on x? I mean, x is the innermost of my three my triple integrals. So what's my lower value for x? I don't think so. Hang on. Maybe I was right. You were right. It is. I was thinking about the 0, which we're going to use later. So say again what you said, Nathan. Yeah, the square root of 1 plus r squared. And the upper limit is 4. Right. The 0 is going to tell us information about another piece right over there. But this value is already bigger than 0, right? 1 plus r squared. The square root of 1 plus r squared is already bigger than 0. All right, how about limits of integration on r? That's going to actually be 0 for a lower limit of integration on r, right? Okay. What about an upper limit of integration on r?
You put 4 in for x and solve for r?
You got it. All right, so if we take this equation, that construction's really loud out there today, isn't it? Okay. If you take this equation and you plug, say again what you said for me. Plug.
Solve for r, so you plug 4 in.
So actually, if I wanted to, I could take this equation and it would be a little bit friendlier. So I'm going to put 4 in for x and solve for r. So what am I going to get? Oops, that's equals, not minus. Yeah, square root of, not 17, 15. Yeah, square root of 15. And then theta? 0 to 2 pi. You got it. Okay, so now we've sort of done half of the problem, right? Because these problems just told us that we did the whole problem because all it told us to do is set it up. But we weren't given an equation inside here that we actually had to integrate. So that's our next step. We're going to be given an equation that we're going to actually integrate after we do these change of variables is what we're actually doing. All right, so our next set of examples are in fact going to have us do both of those directions. We're going to set up and evaluate the indicated triple integral and it's going to say in the appropriate coordinate system. Now I will say that in your homework with these directions like this, I was careful to not just select only the ones that want you to use cylindrical coordinates. So if you see yourself finding one, you're going, I think rectangular would work better for this, then you're probably right. There are some in there that are actually for use in rectangular coordinates, not just in cylindrical coordinates, okay? So don't just look at it and say, cylindrical coordinates, that's the section I must be doing that one. Not necessarily. All right, here's our first one, number 6. A triple integral over the region Q of z e to the square root of x squared plus y squared dv where Q is the solid inside x squared plus y squared equals 4, and outside x squared plus y squared equals 1, between z equals 0 and z equals 3. So you all know perfectly well I don't draw, but the visual for this is not hard to think about, at least. What is this image that it's describing? So what do you see, Tally? Like a pipe, okay, or maybe like a if you want to think about like a paper towel roll or a toilet paper roll. So it's got some thickness to it, right? How do we know that it has thickness to it? Yeah, it's from, well, but the 0 to 3 is not the thickness. What is 0? Let me just say what is the 0 to 3? The 0 to 3 is the height. Good. What's the thickness? The circumference differences, right, for your circle. So this circumferences are actually between 1 and 2, right? Or the radius, I should say, is between 1 and 2, not circumference. But the radius goes between 1 and 2. So you've got sort of the inner radius of the cylinder is at 1, the outer radius is at 2. So you've got something that looks like a paper towel roll. Okay? Everybody good with that? Okay. We got to figure out, obviously this makes sense to do in cylindrical coordinates because we just verbalized an entire cylinder, didn't we? Yeah. And we have this image in our mind of what it looks like. So we're going to turn this into cylindrical coordinates with which variables being replaced? X and Y, absolutely. And how do you know? Tally, you said it first. How do you know? Yeah, right here it has x squared plus y squared here again. So this is going to be my r squared, right? Okay, so let's actually take a look then at the limits of integration that we're needing to do. You know what? Let's do the limits of integration to start with on r. I think that one actually works pretty well because I've already circled the pieces that are related to that. My limits of integration on r, what are those going to be? 1 and 2, right? Because we've actually got this going from, oops, hang on, wrong button. This one's going from r squared equal 4. This one is at r squared equal 1, so r goes from 1 to 2. And that's my in-between, or my second integration that I'm looking at. What about my theta values? Nathan, you like these ones, right? 0 to 2 pi. They do work out nicely. So all we have to deal with is my limits of integration on z. Or, I'm sorry, on yeah, z. That's the only one I have left, right? And they actually told us that one, didn't they? We don't even have another equation going on in this one. This one actually is fixed. That's actually very friendly. We do need to change our equation. We haven't done that yet because we weren't given equations on the previous problems. I have z e to the square root of x squared plus y squared. What in the world does that become? Z e to the r, and then you mentioned another r. Why? Right, because of the r, and then dz, dr, d theta. So far, so good? But is it? It will be, but not in this step of it. Yes, we are going to have, you're right, Caleb. This will be an integration by parts, but we aren't in this step doing integration by parts. The first inside integral right here, I did this last time, so I'm going to continue to do this. This integration right here is actually with respect to z. So with respect to z, what do I get? Right. And I'm going to evaluate that at 3 down to 0. So what's that going to give me? 9/2. And then the other component of it will be 0, because if you let z equal 0, it goes away. So I have 9/2 now, and then I have e to the r times r. And now I'm going to go back and put all the integrations that I just left off from earlier. And I've got the dr d theta. Okay, so this is where we were. So now is your step to do integration by parts, right, Caleb? All right, so this step right here is going to be integration by parts. I've got u du, v dv. What's going to go where?
Can we just pull the 9/2 out first?
Yeah, we can. So can I put it in the very front? Will that be okay with you? Okay, yep, we don't have to have the 9/2 in there. All right, so ignoring the 9/2 now, what do we have?
R for you.
Yep, that looks good. So then du would be dr. What else do I have? dv is equal to e to the r dr. So what's v? E to the r. I had no idea how important integration by parts was. It just keeps coming back up, doesn't it? That and u substitution. All right, so we're going to use integration by parts. So how does that work? Remind me what I'm going to write down next.
uv minus the integral of v d.
Okay. All right, so uv is the r e to the r. V du is just e to the r. dr. I'll go back and add more of the limits of integration and everything in a minute, but let's go ahead and take this integration. So what would that be?
You just do that.
Yeah, just minus e to the r. And I'm supposed to be evaluating this from 2 to 1, right?
Yep.
Okay, evaluated at 2, what do I get?
E squared plus
2e squared minus e squared. Evaluate at 1 and I get not 2e. E minus e, so that actually ends up being 0, right? That piece of it. What about the 2e squared minus e squared? What's that become? That's just e squared. So all that work for a simple little e squared is my value right now. All right, and at the very front of this, I need to include all of those details, including that 9/2 that we pulled out at the front of every piece of this. This is d theta, and then finally I've got the d theta with the 9/2 integral from 0 to 2 pi. All right, integral from 0 to 2 pi, what's the integration of e squared?
theta times e squared.
Yeah, theta times e squared, which I'm going to evaluate at 2 pi down to 0, times my 9/2, you bet. So what will this be?
9 pi e squared.
9 pi e squared. That's right. Oh, that's good. That's what I have written down for the answer. That's always nice. Any questions on that one?
What did we just find in real life?
We don't have a visual for what this is because it's fourth dimensional. Yeah, so hold tight. I believe it's in chapter 15, which is our next chapter where we're going to do applications of this. Okay. Okay. Number 7, same directions. And we're going to change our information. We're going to do the triple integral. Actually, let me put it up here so I have some more space to write. Over region Q of 2x dv, where Q is the solid between z equals the square root of x squared plus y squared and z equals 0. And inside x squared plus y minus 1 squared equals 1. All right, so which variables am I eliminating? X and y. So right up here, I find out that the first equation that I have is that z equals what? R. I also know that z is equal to 0. So that gives me the limits of integration on z, which is the one remaining rectangular coordinate in my cylindrical coordinates. All right, so I'm going to go from, what I say, 0 to r, right? At the end, I'm going to have r dr, r dz, dr d theta. All right. What are my limits of integration on theta? They're actually only 0 to pi this time. Any idea maybe why? What do you know about z? Z has to be positive, so we are where? Yeah, we're at 0 to pi, so we're in the positive. And then also we've got this other detail about the inside of my circle to deal with, but we were only going from 0 to pi on this one. And then we have to deal with our limits of integration on r. Well, we haven't done anything with r yet. We recognize, of course, that r's lower limit is 0. But this other equation tells us what my other limit for r is. Actually, it's going to tell me my limit of 0 for r as well. But let's take a look at taking this other equation and see what we do with this one. So in order to, and this is going to come back into what's going on in section 7 when we do this, so this is helpful information. We're going to take this equation and we're going to expand it, okay? So this would look like x squared plus what? Plus y squared minus 2y plus 1 equals 1, and then of course my 1's go away, right? We also have the x squared plus y squared in here. So what's x squared plus y squared? R squared. Minus 2 times y. Well, what's y? In terms of r's and thetas. R sine theta. All right, so I've got an equation now in terms of r and theta. And if you take a look at what's here and you wanted to actually solve it for r, what would you do?
Just factor in r and add a little bit.
Factor out an r. And so then here's that lower limit r equal to 0 we already said we knew we had, so it's confirmed. And this other one is that r equals 2 sine theta, right? So that's my lower and my upper limits of integration on r. R goes from 0 to 2 sine theta. This is the first one we haven't had r be a fixed quantity. The context is just a little different. All right, I'm supposed to be integrating 2x, so 2's fine, and if you don't even want the 2 in there, you can pull it out to the very front. But what's the x going to be? R cosine of theta. So I actually have r squared inside here now, right? Yeah? Okay. All right, so let me just do one step real quick. Let's pull the 2 out in front because we can. All right, so let's clean up just a touch, make it a little easier to work with. We're going to integrate r squared with respect to, I should say r squared cosine theta. Yes, with respect to z. So what is that going to give me? Z times that, you're right. So I've got z r squared cosine of theta, and I'm going to be evaluating this from r to 0. So what's going to happen? I'm going to get r cubed cosine of theta. Everybody good with that? So I'm going to go back now and I'm going to put in the limits of integration and the 2 at the front. So I've got the 2 integral from 0 to pi, from 0 to 2 sine theta. Now what? Integrate with respect to r. So what's the integral of r cubed cosine theta with respect to r? One-fourth r to the 4th cosine theta. Very good. And I'm going to evaluate this at 2 sine of theta down to 0. Okay, when I evaluate at 0, it's still 0 because 0 is going in for r. But if I evaluate at 2 sine theta, what's going to happen? Let's start with the 2. What's going to happen to the 2 when I plug the 2 in?
16.
I'm going to get 16 with the 1/4 in front is going to become a number 4. Okay, good. What's going to happen with the sine theta? Sine to the 4th of theta, cosine theta. Okay. So at the very front, again, I've got this 2 integral from 0 to pi. The end is d theta. If we wanted, we could pull the 4 out in front with the 2, and we might as well. We've already pulled the 2 out, right? So let me move the 4 to the front and make this an 8. And then it's going to hit us twice in one day, isn't it? Maybe more. This is, again, an integration, but it's not by parts this time. Why not?
Well, because that wouldn't really solve the problem.
Integration by parts is not needed here. We can do it with u substitution. Do you know why? Yeah, it's really because of the power of 4, right? Notice right here, if I were to let u equal to sine of theta, what would du be? Cosine of theta. So we have one of these, it's not advanced, I guess, really, but it's one of these different integration techniques coming into play, but this one's u substitution. So I actually have u to the 4th in my problem that I'm going to integrate. So I'll leave my limits of integration off for the moment, but I'm going to be integrating u to the 4th du. All right, so I have the 8 at the front. I've got u to the 4th du, so that becomes what? 1/5 u to the 5th, but it's not really u. It's, since it's now 8/5 with sine, right? Sine to the 5th of theta, and theta is going from 0 to pi. This is 0. Isn't it? All that work for nothing.
Literally nothing.
Literally nothing at the end. Zeros at the end. All right. One more problem, I think. I think this is the last one in our section. Yeah, one more. All right, different directions. We're going to change it up just a little bit. We're going to evaluate the iterated integral after changing the coordinate system. So the original integral goes from 0 to 1, and then 0 to the square root of 1 plus x squared. Sorry, it's supposed to be a minus, not a plus. Minus here. And then the integral from 1 minus x squared minus y squared to 4 of the square root of x squared plus y squared dz, dy, dx. Got all the details there. We don't have the tools to do this in rectangular coordinates, even if we wanted to. It's not conducive to that method at all, right? It would be awfully ugly. So cylindrical coordinates are very nice because we see a lot of x squared plus y squared kind of features in this problem, right? So let's take a look at a few things. We are, in fact, like I said, going to use the x squared and the y squared to be replaced with the r and the theta. So the first thing that I'd like for us to take a look at is the innermost integral limits. In particular, we've got one limit that says z equal 4, and you've got the other limit that says z equal to 1 minus x squared minus y squared. So what will that piece become? 1 minus r squared, right? Good? The second limits of integration right in here, the ones that are sort of the in-between limits of integration, are on the variable y, according to the structure at the end. So this one actually tells me that this is going from y equals 0 to y equals the square root of 1 minus x squared. All right, so y equals 0 is going to tell us that r is going to go from 0. If y can equal to 0, then r can equal to 0 as well. This equation right here, I can solve this, or not solve, I can restructure this. So this says y squared equals 1 minus x squared, or x squared plus y squared equals 1. So this actually tells me then that r squared is equal to 1, or r is equal to 1. When we take the square root, right? So that gives me limits of integration on r. So now I had limits of integration on z. I have limits of integration on r. And now I need to talk about taking a look at what happens with respect to theta. All right. Taking a look at the original function, hang on just a second. I'm going to draw a picture. What I actually want to look at is this two-dimensional picture that I'm getting for x and y out here, because I haven't dealt with x at all yet at this point, right? I've sort of ignored that outermost integration. So my x value is supposed to be going from 0 to 1. So here's 0, here's 1. What in the world does the graph look like if it goes from 0 to square root of 1 minus x squared? What is that graph? It's a half a circle, and if you aren't sure, I mean, you can take a look over here. This is the full circle of it. Why is it only half the circle?
It's positive square root.
Right, it only goes from 0 to the positive square root, not to the negative. So if it went the whole circle, we'd go from negative square root of that value to the positive square root of that value. So this actually would just be the the half circle, the semicircle up here like this, right? But is it the whole semicircle? It's just 0 to pi over 2 right here. Why? Yeah, because x only goes from 0 to 1, correct? So if x is only going from 0 to 1, then I shouldn't be in quadrant 2. So this tells me what to do for my limits of integration on theta. So this is my first time that I haven't had a whole pi. I didn't have a 2 pi just a minute ago, so it's not always 0 to 2 pi. This one would be what? Yeah, so this theta goes from 0 to pi over 2, and once again, pictures save the day, don't they, to help us figure those pieces out. All right, so we can set up this set up this triple integral now in the cylindrical coordinate system. So I have we said 0 to pi over 2 for my limits on z or on theta. My limits on r was it 0 to 1?
Yes.
Okay, and then the limits on z were from what? Okay. Do you have them all in there okay? How do we know that it's 1 minus r squared to 4 and not 4 to 1 minus r squared?
1 minus r squared. 1 minus x squared minus y squared was on the bottom.
Okay, that's part of it. It's also a smaller value. If my r values are going between 0 and 1, then I'm going to get values that are going to be smaller. So the values themselves are going to be smaller than the value at 4. Okay. All right, so I'm going to take my original function, which was what?
Square root of x squared is y squared.
Square root of x squared plus y squared. That was the original function inside of my integration. So what will it be? It'll just be r. And then I've got the r dr, it's r dx dr d theta at the end. I said x and I wrote z, so that's good. I got the right letter written down. But yes, dz dr d theta. Thank you. And of course, I've got 2 r's there, so I'm going to save myself a step and just write this as r squared. Are you guys good with that?
Yeah.
Okay, so this is r squared dr dz dr d theta. And we're going to take an integration with respect to z, which is going to give me
CDR squared.
sorry, this is squared somehow got erased. Yeah, zr squared. And I'm going to evaluate that at 4 down to 1 minus r squared. So I evaluate at 4 and I get what? 4r squared. And then if I evaluate at 1 minus r squared, I get what? I think r to the 4th. R squared minus r to the 4th. And if I simplify, that gives me what? 3r squared, and then what? Plus r to the 4th. Good. All right, so that's everything inside of the, inside of the pink rectangle. And then we're going to go back and put our limits of integration from 0 to 1 and 0 to pi halves on each step. Don't forget that part of it. And at the end, dr d theta. All right, next integration is with respect to what? R. So 3r squared becomes r to the 3rd. R to the 4th becomes 1/5 r to the 5th. And we're going to evaluate this from 1 down to 0. So if I evaluate at 1, what do I get? 1 plus 1/5, which would be 6/5. And evaluating at 0 gives me 0. So and then I've got the integral from 0 to pi halves, d theta. So what's the integral of this with respect to theta now? 6/5 theta, evaluated at pi over 2 and 0 gives me 3 pi over 5. Very well done. Any questions on this one? All right. me write in the homework for you. Let me preface this by saying that this list looks really long, but like 6 of them at the beginning are just converting into coordinate. They aren't integration. They're just changing variables around. That's all they are. Okay, so very quick, very easy problems at the very beginning. So this is page 954. Numbers 2, 4, 6, 8. Those are, and then 10 and 13. I think all 6 of those are the ones that are just converting. And then 15, 18, 22, 25, 28, 33, 36, 42, and 45.